Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are starting a crucial deep dive into Unit 5, Magnetism and Matter. The mission is, well, it's simple. We're going to build a clear, exam-safe foundation that hopefully removes all fear of this topic, even if you find physics a bit challenging. Okay, let's start with something we see every day, a curiosity hook. Think about a simple compass. I mean, we all know magnets stick to the fridge, but how does that tiny piece of iron, the needle, manage to point north? Consistently, year after year.
It really does feel like magic, doesn't it?
It does. There's no battery, no wires. What's going on there?
When I was younger, I honestly thought magnets were just special stones, with some kind of permanent, inherent pull. It's hard to imagine what keeps that needle so perfectly aligned.
Precisely. And here is where the physics gets really interesting. If you take a piece of ordinary non-magnetized iron, a nail, for example.
Okay.
It contains the exact same electrons, the exact same atoms, as a really strong permanent magnet. There is no special ingredient.
The very same.
The very same. The only difference is not the material, but the organization, the atomic alignment.
Alignment.
Yes. And here's the surprising part. You can actually make that nail weakly magnetic just by giving it a few hard strikes with a hammer while holding it in the Earth's magnetic field.
Wait, really? Just by hitting it with a hammer? That sounds a bit crude. How does a mechanical shock create magnetism?
Because that shock gives the tiny atomic magnets inside just enough energy to jiggle around and align themselves with the Earth's field. It proves magnetism isn't some hidden property. It's all about organization.
So it's about getting trillions of tiny things to work together.
Exactly. So why does this alignment matter so much? Let's unpack the core idea. At the most fundamental level, magnetism is a force created by moving electric charges. That's it. Full stop.
Moving charges.
Moving charges. If a charge is stationary, it only creates an electric field. But the moment it starts moving, poof, a magnetic field appears as well.
So in every magnet, whether it's a bar magnet or an electromagnet, there must be electrons moving somewhere. That movement is like a tiny electric current.
Absolutely. That is the core insight. Magnetism emerges from electric currents. It could be a literal current in a wire or these hidden atomic currents from electrons spinning. No motion, no magnetism. To visualize this, let's use an analogy. The whirlpool effect. Imagine a river of charge.
Yeah.
When electrons move in a circular path like water spinning in a whirlpool, they create these swirling forces around them. That invisible swirl is the magnetic field.
That makes sense. It creates a disturbance. But what led scientists to connect this whirlpool idea to, say, a lodestone? They seem so different.
Well, that's the fascinating history, isn't it? For thousands of years, magnetism was just magic. Then, around 1820, Ørsted discovered that an electric current could deflect a compass needle.
Ah, the first connection.
The first solid connection. Then Ampere, Biot, and Savart proved it. Moving charges or currents produce magnetic fields. That discovery unified electricity and magnetism forever. Now let's build a strong mental picture for the exam. Picture billions of tiny electrons in an atom. Each one is spinning like a microscopic top.
Okay, like tiny spinning balls.
Exactly. And each spinning electron creates its own tiny invisible magnetic field, a little halo of force. We call it an atomic dipole.
So every atom has these little magnetic halos.
Yes, but in normal iron, these halos are all pointing in random directions. It's complete chaos. They all cancel each other out.
Right.
But in a strong magnet, trillions of these halos are forced to line up, all pointing in the same direction. Imagine coins stacked perfectly on their edge. This massive combined effect is the strong magnetic field we can actually feel. Okay, so that's the simple picture. Now let's see how insert formally defines all this, starting with the classic bar magnet. Can you please read the verbatim definition for the poles?
Certainly. Insert states, when a bar magnet is freely suspended, it points in the north-south direction. The tip which points to the geographic north is called the north pole, and the tip which points to the geographic south is called the south pole of the magnet.
And what about how they interact?
It adds, there is a repulsive force when north poles, or south poles, of two magnets are brought close together. Conversely, there's an attractive force between the north pole of one magnet and the south pole of the other.
Excellent. This classic behavior confirms that the bar magnet is a magnetic dipole. Now let's talk about the field lines. This is crucial for marks. Step 1. The iron filings pattern shows the dipole structure. Step 2. The lines show direction. Outside the magnet, they exit north and enter south. Simple enough.
Right, that's the standard picture we always see.
But step 3 is the most crucial part. Unlike electric field lines, magnetic field lines must form continuous closed loops. They can't just start or stop.
Those loops. So what does that mean for what's happening inside the magnet?
It means they have to complete the circuit. They run from the South Pole back to the North Pole inside the magnet.
Ah, I see. So it's a complete unbroken loop.
Exactly. And step 4, just to recap the properties, the direction of the field B is tangent to the line, and the lines never intersect. Now, this closed-loop behavior isn't just an observation. It's a fundamental law of nature, written down as Gauss's law for magnetism. Could you state that law for us exactly as an insert?
Yes. The formal statement is, the net magnetic flux through any closed surface is 0. And the formula is the integral of B dot dA equals 0.
Right. That formula looks intimidating, but the concept is simple. It just means that for any closed surface like a sphere, the amount of magnetic field lines going out must exactly equal the amount of field lines coming back in.
So there's no net flow out of the box.
Precisely. And this leads to a profound conclusion. Isolated magnetic north and south poles, magnetic monopoles, do not exist. You can't have a source of field lines without a sink.
Which are completely different from electricity, where you can have an isolated positive or negative charge.
The single biggest difference. Absolutely. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.litcom. Now, let's use a simple worked example to make this a bit more real. Let's talk about torque on a compass in Earth's field.
Okay.
Imagine a small compass needle with a magnetic moment, mu, of 0.5 amp-meter squared. We place it in Earth's very weak magnetic field, about 50 microteslas, and let's say it's at an angle of 30 degrees.
All right.
The formula for the twisting force, the torque, is tau equals mu b sine theta. If you calculate that, you get a tiny number, 1.25 times 10 to the minus 5 Newton meters.
That's a very small number.
It is. But forget the number for a second. What does it mean? It means even Earth's weak field exerts a persistent, gentle, twisting force on that needle.
And it keeps twisting until the angle is 0.
Exactly. The torque acts until the compass aligns perfectly with the field lines. When theta is 0, sine theta is 0, and the torque vanishes, the needle comes to rest.
So that's why it settles down pointing north. The torque is just the mechanism that forces the alignment.
That's it. It's not magic, it's torque. And connecting this to the bigger picture, this whole unit follows from Unit 4. We learned current creates a field, and now we're exploring how that field interacts with matter. This will lead us right into understanding different magnetic materials. Okay, now let's tackle a few silent killers, common misconceptions that cost students marks.
Ready?
Misconception 1, poles are charges. The wrong idea is that a magnet has a little blob of north charge at one end and south charge at the other, just like electric charges.
I have to admit, I definitely used to think that. I thought if I broke a magnet in half, I'd get a separate north pole and a separate south pole.
And it's a very logical thought. But it's wrong because, as we said, monopoles don't exist. If you break a magnet, you just get 2 new smaller magnets, each with its own north and south pole.
Right, so breaking a magnet just makes 2 smaller, complete magnets. You can never isolate a pole.
Correct. Now, misconception 2. Earth's poles. The wrong idea is that a compass's north pole points to Earth's north magnetic pole.
That sounds right, though. Like poles repel, opposite poles attract. Right. Exactly. You've got it. The tip of your compass is the north-seeking pole. Since opposites attract, the magnetic pole up near the geographic North Pole must actually be a...
That's the magnetic pole.
Of course. Yes. The naming is just a historical accident. It seeks north, so it must be attracted to a magnetic south. And finally, misconception 3. Field lines are force lines. Students assume the magnetic field line shows the path a charged particle will follow.
But that's only for electric fields.
Precisely. For magnetic fields, the force is given by F equals QV cross B. That cross product means the force is always perpendicular to the field line.
So the particle gets pushed sideways, not along the line. That's why they move in circles or spirals. So calling them lines of force is misleading.
Very misleading. The force vector and field vector are almost always perpendicular. Now, to make sure this all sticks, here are some memory hooks. First, the mnemonic. Moving implies magnetic. Simple. No motion, no magic.
Moving implies magnetic. Got it. Next, the physical gesture. Use your right hand. Curl your fingers in a circle. That's the moving charge or current. Your thumb automatically points in the direction of the magnetic field, B. Use it all the time.
Right-hand rule. Fingers are the current, thumb is the field.
Perfect. And a little association for later. Paramagnets are forgetful. When the field is gone, they forget their alignment. But ferromagnets, they have a strong memory and stay magnetized. All right, let's summarize this with 3 short exam-safe points. 1. Magnetism is fundamentally created by moving electric charges, whether in a wire or the hidden atomic motion of electrons. 2. Magnetic field lines are always continuous closed loops. They exit north and enter south outside, but continue from south to north inside the magnet. And 3. Gauss's law for magnetism tells us the net magnetic flux through any closed surface is 0, which is the mathematical way of saying that isolated magnetic monopoles do not exist. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
And that is ProfSam.com, correct?
Yes, ProfSam.com. Keep studying hard and apply these concepts. We will meet next time for a deep dive on magnetization. All the best with your preparation.